So in this discussion, this is discussion number 4, and we are going to talk about what Professor covered in last week. So it's basically we're going to talk about the offset current. I'll explain what's the offset current later, but I think Professor has mentioned this is related to the bias current, and also we will design some op-amps using some constrained op-amps. So first, just recap the input bias current. So the input bias current will have a bias current, I bias, in both terminals. So you have a bias current in plus terminal as well as a bias current in the minus terminal. And because of the bias current, so for example, if you have two bias current here, let me change it. So because you have a bias current here, if you connect the resistor to the plus terminal, let's call it, you gave it a VI. Because of the I bias, there will be a voltage drop between the resistor. And in this case, your actual V plus will not be equals to V minus. Your V plus will not be equals to VI. In that case, your V out will not be the desired value you want for your circuits. So this is how the input bias will affect your circuits. However, for the input bias, I think Professor mentioned all of them are just this case. So in last week's lecture, all our bias current will have the equal value. So your I bias 1 always equals to I bias 2. However, there will be offset voltage. So let me define what's the offset voltage. First, I will define IB, which is a common mode voltage. Common mode currents. It's just I bias 1 plus I bias 2 divided by 2. So this is a common mode bias current. And the offset current is just a difference between two bias currents. So it's I bias 1 minus I bias 2. So this is the definition of offset voltage. So in last week's lecture, we will have offset voltage equals 0. So if offset equals 0, that means I bias 1 equals to I bias 2. In this case, you can always just compensate the bias current by adding this resistor. So if you have a resistor RB equals to R1 in parallel with R2, you can just eliminate the bias currents from this op-amp circuit. However, if your IOS, so offset currents, not equals to 0, you will still have your input bias current cannot be eliminated. So you will still have some effect on the output voltage. We'll explore this in later slides. We'll explain this. Let's see here. So now consider you have an offset current. So IOS is 10% of I bias 1. That means your IOS is just 0.1 times I bias 1 equals to I bias 2 minus I bias 1. So you have actually I bias 2 equals to 1.1 times I bias 1. So in this case, even though you have a RB is equals to R1 in parallel with R2, your V out is not 0. And we will calculate what's the actual V out you will get. What's the non-zero value of V out you could get. So we will do this using superposition. So right now, your I bias 2 equals to 1.1 I bias 1, right? We can just separate this I bias 2 into two different current source. So the first current source will have I bias 1, and the second source will have 0.1 I bias 1. So we just separate the bias 2, the 1.1 I bias 1 into two different sources, and when we use the superposition, so we calculate each source one by one. So this will be our first case. So in first case, we just use I bias 1. For our first case, we calculate what's the voltage in the first case, and we use the 0.1 I bias 1 in the second case. We calculate what's the voltage V out in the second case, and your final V out will just be the sum of this outputs in two cases. So that's how the superposition works. So in first case, we'll just have I bias 1. We'll just have just this current source in the circuit. So our circuit will just look like so this is our circuit will look like. I'll use IB1 to represent I bias 1. So this is the first case, just using IB1 as our IB2. In this case, this is just what we covered in last week's lecture. By just having RB equals to R1 in parallel with R2, we can successfully eliminate our bias current. So in that case, our V out will just be 0 volts. There will be no bias current in this circuit. They are all like eliminated by the compensation of resistors. This is just the first case. So in first case, we will have V out equals to 0 volts. And the second case of the superposition is we will have I bias 2 equals to 0.1 I bias 1. So we will have 0.1 I bias 1 here in the second case. And there will be no I bias 1 because we include the current source in plus terminals in the first case. So in second case, there will be no current source in the plus terminal. So that's all we have. We just have a 0.1 I bias current source in the negative terminal. What's the corresponding V out we could get? So because right now the VI is directly connected to the plus terminal, and there will be no current source connected to the ground. And this is an ideal open. That means your input voltage is actually infinity. So I plus will equals to I minus equals to 0 amps. There will be no current flowing through the plus terminal. That means the current that's flowing through RB equals to 0. There will be no voltage drop across RB. So VI will just equals to V plus. So these two are equal. If we ground the VI, that means V plus will just be same as 0 volts. And for ideal open, V plus always equals to V minus. That means you will also have 0 volts at this node. It's still 0 nodes. It's grounded. So you have for the R1 resistors, you have both 0 volts on two nodes. There will be no voltage drop between R1. So the R1 will have no current. So the current is 0 amps. All of the 0.1 I bias will just flowing through R2. So the current flow R2 will just be 0.1 I bias 1. So what's the corresponding V out? So V out in the second case will just be voltage at V minus, will just be V minus. So this voltage plus 0.1 I bias 1 times R2. So if we have the bias current, like our R2 is like 1 megohms, and we want our IB to be, let's choose a value for IB. I'll use IB is just choose a value. I'll use I bias 1 equals to 200 nanoamps. So in this case, just assume the bias current is in nanoamps range. Our final output Vout will just be 200 nanoamps times the 1 megaohms, which will give me 20 millivolts. So this is output voltage in second case. So our total Vout will be the output voltage in first case plus the output voltage in second case, which is 0 volts plus 20 millivolts, gives us 20 millivolts. So just by having like 10% of the offset voltage, of offset current, just have like 10%, a super small offset current, you will have a 20 millivolts voltage offset. So you'll have your offset current will affect your output voltage. Furthermore, so if we have both offset current and offset voltage, we want to know if we have both the offset currents and offset voltage, we want to know what's the DC voltage, what's the final Vout we could get. So same, we'll use superposition. So we'll consider VOS and IOS one by one. So first case, we'll just include the VOS in our circuits. And the second case, we'll just include the IOS. So from last week, for the offset voltage, if we have a VOS is 2 millivolts, our Vout will just be the AV closed loop times the VOS. So this is the superposition of first case. So there will be no offset current or bias current. We just have a offset voltage in our circuit. So if we have just the offset voltage 2 millivolts, our output voltage will be the closed loop times VOS. And the gain, the closed loop gain of this circuit is just 1 plus, because this is a non-inverting amplifier, so it's 1 plus R2 divided by R1, which is close to 100. So R2 is 1 megaohms, R1 is 10 k ohms. The ratio is like 100. So the offset voltage will give us a Vout 100 times 2 millivolts, will give us 200 millivolts. This is what we can get from the offset voltage. And the second case is we have IOS and no VOS. So just considering what's the offset current we'll get. And from the last slide, a 10% or 0.1 offset current will give us Vout is 20 millivolts. So the worst case DC voltage will just be Vout total equals to Vout in the first case plus Vout in the second case. So the worst case DC voltage we can get is 200 millivolts plus 20 millivolts is 220 millivolts. This is a worst case DC voltage we can get for this compensated circuit. Next is the constrained op-amp design. So by mean constraint here, because in real life, we will never have ideal op-amps. So all the op-amps we have, it has like finite gain and also finite bandwidth. So just by giving you some constraints or the requirements or the performance of the op-amps, you just use the non-ideal op-amps to design your circuit. So you have to make sure your design or your input signals satisfy all the constraints the op-amp has. So for example, for this is a non-ideal op-amp. I have it Ft equals 20 megahertz. So the unity gain frequency of the non-ideal op-amp is 20 megahertz. And the op-amp has a slew rate of 10 volts over microsecond, which is just 10 times 10 to the 6 volts per second. And it has output saturation. So the maximum output Vout it has is 10 volts. So that's the constraints the op-amp has. And then I want the circuits to have I just connect the op-amp with some resistors to construct a negative or non-inverting configuration. So this is a non-inverting op-amp. So right now the op-amp has AV equals to 10 volts over volts. So basically our R2 over R1 is like 10 or 9. And I also have my VI is 0.5 volts. With these three constraints, I want to know what's the maximum frequency signal that can be amplified without distortion occurs. So just by saying this distortion occurs, you may know this must relate to the slew rate. So because only the slew rate could distort your signal. So if you want to design a circuit, you must make your circuit or your signal satisfy all three constraints, which is hard because if you want to design a circuit and at the same time just satisfy all three of them is hard. So for the design specs, we'll just choose one constraint, like choose one of them or two of them, and then using just one of them to design your circuit. Once you finish your design, put your design back to the configuration and check, does it satisfy the other two constraints? If it's satisfied, your design is correct. If it does not satisfy, you may need to redesign your circuit. That's how we design a circuit. So first, just by seeing like distortion occurs, I think this is mostly related to the slew rate. So I'll just using the slew rate to finish my design first. So our slew rate is 10 volts or over microseconds, and the slew rate is usually dV over dt. The output voltage is a slope of the output voltage. If we want to have our output voltage not distorted, that means your slew rate must be greater or equal to dV naught over dt. By just inputting the sinusoidal signal, so I have a sinusoidal signal here, your output must also be sinusoidal. So your V out is actually a sinusoid. It will have a magnitude V out times cosine omega naught t. So your dV naught over dt will just be omega times V out cosine omega naught t. To have an undistorted output, this derivative must be less than or equal to your slew rate, which is 10 volts divided by microseconds. What's your output voltage? Because the gain, the closed loop gain of the circuits and also the input is given. So your V out will just be AV times VI equals to 0.5 volts times 10, which is 5 volts. So just using these two equations, so basically plug the V out equals to 5 volts back to your slew rate equation, we can calculate what's the omega max. So omega max will just be the slew rate divided by 5 volts times, yes, it will just be slew rate divided by 5, which will give us 2 times 10 to the 6 radians per second. Converted back to the hertz, it will just be omega max divided by 2 pi, which is 318 kHz. So just by looking at the slew rate requirements, the maximum input frequency we can use is 318 kHz. And this is not finished. You have to put your design back to the constraints and to check, does your result satisfy them or not? So for here, our maximum frequency is 318 kHz. So this one is much less than FT, which is 20 megahertz. Okay, I will not use FT. So first, from this design, if we have FT equals 20 megahertz, this is a unity gain. That means the gain equals to 1. So what's the 3 dB bandwidth? What's the cutoff frequency? We can use the GBW. The gain bandwidth product is a constant. So 20 megahertz times 1 will equals to the closed loop gain 10 will equals to 10 times F 3 dB. So your 3 dB bandwidth is actually 2 megahertz. And we can compare this with, we can compare your 318 kHz with the 3 dB bandwidth. This is much less than 3 dB bandwidth. So in this case, that means your AV in this circuit is 10. So our assumption is correct, because right now, right here, we use AV equals 10 for our circuit. So in this case, we assume the input frequency is actually within the range of a constant gain. So this is your F3 dB. When design our circuit, we already made an assumption that your frequency is within this range. So you can have a constant AV equals 10 for your circuits. So once you're finished, you double check it. Yes, your assumption is correct. The result you get is actually within this range. So your AV is actually just 10. You are right. So, and the frequency is not related to the maximum output. So we don't care about this. So by just double check this, so your design like 318 kHz is satisfy the slew rates check. It also satisfy the unity gain bandwidth requirement. It within the 3 dB bandwidth or FT. That means this design is correct. Your design is like satisfied all the constraints. It's a good design. The second example, as for the same non-inverting configuration, so non-inverting amplifier, I have my DC gain is 10 volts. I have input frequency is 20 kHz, the same requirements or same constraints of the op-amp. I want to know what's the maximum input signal amplitude we can use without distortion occurs. So distortion occurs, another slew rate. So to design a circuit, first, I made an assumption. So I assume AV is 10. Actually, we don't need to assume that. First, the input frequency is 20 kHz. And we calculate what's the 3 dB bandwidth, or what's the cutoff frequency is 2 megahertz. This is much less than 2 megahertz. So for your amplifier, you will have a constant gain at this frequency. So your closed loop gain is always 10 at 220 kHz. This is not a consumption. This is the result, what we know. And also to find what's the maximum signal amplitude, we care about the slew rate. So for the slew rate, we have the same equation, dV naught over dt equals to omega times V naught cosine omega naught t. So the maximum and omega naught is omega times A V times VI times cosine omega naught t. So the maximum VI we can get is just the slew rate divided by omega times AV. Just plug in numbers. Our slew rate is 10 times 10 to the 6 volts per second over omega is 2 pi times 200 kHz times your AV. Because of this, your gain is just 10. So your VI max would just be 796 millivolts. It should 0.796 volts. So finish your design, and then you have to check it with the other constraints you have. So we finished, our design is satisfied those two. When we design it, it's already satisfied. And we have to double check our output, our result with the last constraint. The last constraint of the circuit is the V out max is 10 volts. We have to check this. What's if we have VI max is 0.796 millivolts, our V out will just be 10 times VI max is 7.96 volts. This is less than 10. So the last constraint is also satisfied. That means our design or our result is correct. We can have VI max equals to 796 millivolts into the circuit without distortion. In the last example we could have at this, we have the AV is also 10 volts over volts for DC gain. So we have F naught equals to 50 kHz, and the DC gain is 10. Same constraints as before, and we want to know what's the usable input voltage range. What's the voltage range you can have for your circuits? So right now we have 3 constraints. First, FT is 20 megahertz. Our input frequency is 50 kHz. This is less than F3dB, which is 2 megahertz. So your actual gain of your circuit is 10. It's within the constant gain range. So your gain is always 10. This is satisfied. It's within the range. And then I still want to use the slew rate for my design. So my slew rate is 10 volts per microseconds. I want to know what's the input voltage range. That means you have to find what's the maximum input voltage you can have. That's the range mean. So my maximum input voltage for slew rate will just be omega times V naught max, and your VL max will just be omega times AV times VI max. Your omega is 2 pi times 50 kHz, and AV is 10. So you can just calculate your max input voltage using this, using slew rate. So your just by considering your slew rate, your maximum input voltage is 3.18 volts. Just using slew rate, I got this result. And I have to put it back to the other constraint to check is it satisfied or not. If I have VI equal to 3.18 volts, I want to check my VL max. Because my gain is 10, so my VL max is actually 10 times 3.18 is 31.8 volts. This is much larger than 10 volts. So my constraint is not satisfied. That means your design or this input voltage is not satisfied by your circuit. You have to redesign it. So this is not right. So we cannot just using slew rate to calculate our result or to finish our design. We have to use VL max. So if you have VL max equals 10 volts, and because the F is just 50 kHz is within the 3 dB bandwidth, so that means your AV is 10. So if you have maximum output voltage 10 volts and your gain is 10, the maximum input voltage you can get is always V out max divided by your gain is 1 volts. So the actual input voltage range will just be 0 to 1. So this is how we design the circuits. Choose one constraint or choose one requirements to finish your design, and then put your design back to the other constraint to check if it is satisfied or not. If it's not satisfied, you have to redesign your circuit using the other constraint until you got the correct one. So this is how we calculate it. I think this is pretty straightforward. Yeah, this is all we have for this discussion. It's quite short. And then next one, we will have, we'll do some reviews of the semiconductors, the diodes, the MOSFETs, the BJTs, something like that. And for the lab, I think you may saw it or not, we will postpone our pre-lab to due until the end of your lab. So if you are a Monday lab section, your pre-lab is due at 8 p.m. today. If you are a Tuesday lab section, your pre-lab 2 is due tomorrow at 2 p.m. So you will have like extra time to work on your pre-lab. So you can just work on it during your lab time and ask your lab TA about questions. And we will post the lab 2 before the lab session starts. So you still have some time, so don't worry. And if you have trouble accessing your waveform viewer, like A-Waves, we are communicating with the EECS staff to see how it works. We'll give you extra credit if you cannot do the waveform plots. That's okay. Yeah, that's all we have for